So I first of all welcome you to this lesson, and today we are going to discuss pressure as our topic. And one thing that I would like you to know is that pressure is a paper 1 topic for those maybe who are yet to know between paper 1 and paper 2. But because it's a form 1 topic, I just want to discuss pressure the way it is. After going through all these questions that I want you to go through, we have a set of questions here which I like you to follow me with them. Those that we can interact one-on-one. They are those that I have sent them this paper and they have done it. Now, I want us to mark these questions. Then you see where you have gone wrong. Before we continue, this is Ambassador Foundation, and the one presenting is Alex from Loreto High School, Limuru. If you have not subscribed to this YouTube channel that brings you amazing lessons, I don't know, what are you still waiting for? Subscribe as we are moving on. Now, I don't know whether you can see, it was being drawn by one of my students, but I believe she tried her best. Now, in our first question, we are told that a vacuum pump was used to pump out air from a glass tube immersed in liquids as shown in the figure. The figure in question, we have blackboard and then we have the whiteboard. I don't want to use the whiteboard. Most of my followers come from the remote areas. They used blackboard. I don't want to say they are not used to whiteboard. Then for those of you who are used to whiteboard, it is here. Ni mimi ndio sitaki kutubia, lakini I will be using when it comes to calculation, because it is very easier to run whiteboard than to run blackboard. I will be calculating here. You know, it has less friction for me to run it. It's still physics. Now we are saying this. A vacuum pump was used to pump air out from the glass to immersed in liquid as shown in the figure below. After some time, the level of water rose to position X. Mark Y corresponding position for the paraffin level. Give a reason for your answer. Now, if this is the level of water, you know, this is what was used to suck air or to pump air. Meaning what? The pressure applied to both water and paraffin are the same, but the levels will be different. What brings about difference in levels? It is because paraffin and water are of different densities. That is it. You know, all of them will have to conform to this. Let me write here. You know, pressure in liquid is given by rho GH. If pressure in liquid is given by rho GH, so rho is the density, gravitational field strength, and then the height or the depth. Now, the gravity will be the same because it's in the same locality, but the density will vary. And because the density will vary, or it's already different for water and paraffin, water is denser than paraffin, they will have different heights. For them to produce the same pressure, the one with a greater density, that is now the water, will have a smaller height. The one with a less density will have a greater height, so that it can match and produce the same pressure. So if I have to fix this, if the level of water is at this point, then the level of paraffin will be somewhere higher, this part. So if you are placed Y above that, mark for yourself. The reason is because paraffin has less density compared to water, so it has to have a greater height to produce the same pressure like that of water, because it was the same vacuum pump that was used to pump out the air. Define the term atmospheric pressure. Our question number 2. Define the term atmospheric pressure. It's very simple. It is the pressure exerted by the column of air on the Earth's surface. You know, on this Earth's surface, there is air surrounding the surface of the Earth. So the pressure exerted by the air column on the Earth's surface is what we are calling it there, atmospheric pressure. It is greater at the valleys. It is lower at the top of mountains. Now, there is a question here I want us to calculate. I will read it for you. Yours is to listen and to write it down. Then we calculate it together. The height of mercury column in a barometer at the base of a mountain is found to be 760 millimeters, of course, of mercury, and 610 millimeters at the top. So you see, at the bottom 760, at the top 610 millimeters of mercury. Those are pressure in millimeters of mercury. Determine the height of the mountain if the density of mercury and air is 13,600 and 1.25 kilogram per meters cubic respectively. So this thing, it's this way. Let me pick a pen that is doing well. Are you seeing that? At the bottom of the mountain, because the air column is greater, the atmospheric pressure is also greater. We have divided atmospheric pressure over there. At the top of the mountain, the air column is shorter, so the atmospheric pressure is less at the top of the mountain. Now, this formula, rho GH, doesn't only apply to liquids, as most of you are thinking. It applies also to gases. So in short, it's a formula for fluids. Rho GH applies to both liquids and gases. Mark that one. Now, we are here. We have the pressure at the bottom of the mountain and we have the pressure at the top of the mountain. What has brought to the difference in pressure? It is because of the air in between here. So we are going to calculate our pressure at the bottom of the mountain. Then at the top of the mountain, the difference in pressure, of course it is greater here, it is smaller here. The difference in pressure is because of the height of air column in the mountain. So after getting that difference, we apply to rho GH of the air. And the height of the air is simply the height of the mountain. Now let's look here. At the bottom of the mountain, it is 760 millimeters of mercury. You know, when we talk about rho GH, rho the density, g the gravitational field strength, then height in meters. So it's going to be 760 millimeters. So I will divide by 1,000 to give me meters times the density, which is 13,600. Remember, we are dealing with mercury. Then times G10. Up there, I will use 610 times 13,600 times 10. So find this value. Then you find the other value up there. This one is 103,360. I hope you can see. This one is 82,960. All of them are pascals. Pascals. That is it. Then, you see, the pressure is greater here. It is less there. Let's get the difference in pressure. So it's simply 103,360 minus 82,960. 82,960. We get 20,400 pascals. This is the difference in pressure between the lowest part of the mountain and the highest part. What can we do now? This pressure is pressure of the air in between. And remember, rho GH still applies. So I want us to get now the rho GH of the air. Already we have the pressure. So 20,400 should be equal to rho GH. Rho of the air, we have been told, it is 1.25. G is just 10. Then H is the height of the mountain that we don't know. You will have 20,400 is equals to 12 0.5H. So our H, you simply divide across, you will get 1632 meters. That is how it is. That is how you can get the height of the mountain. It's not that difficult. Just follow the steps. For those we are marking together, mark for yourself. Give yourself 3 marks if you have gotten it. Question 3. Give a reason why mercury is preferred as a barometric liquid. Give a reason why mercury is preferred. Why don't we use water, paraffin, and any other liquids? The reason is this. Mercury has a greater or a higher density, therefore requires or produces a shorter column. If you use that as mercury will just require 76 centimeters to measure atmospheric pressure, roughly there. So meaning the tube you will be using, the mercury barometer is in this manner. Allow me to clear this. Mercury barometer, you know how it is. So the atmospheric pressure will push the mercury to rise. So if it is mercury, it will just give us a height of 76 centimeters roughly there. So meaning to provide an allowance, we just use a tube of 1 meter. If you try to use water, you will have to find a tube 10 meters and above. If you use paraffin, it is worse. It will be even more than 20 meters. So the best thing is we use mercury because mercury has a higher density, hence a shorter column. Ukiandika hivyo, kama uliandika hivyo, mark it for yourself. State the principle of transmission of pressure in liquids. It's also called the Pascal's principle. Pressure applied at one part of a liquid or in a liquid is transmitted equally to all other parts of the enclosed stroke enlarged liquid. Pressure produced at one part is transmitted equally. That is the Pascal's principle. We will see its application in a few minutes. Let's get to the next question. I don't know whether it's here. Our next question, I don't know whether it was drawn here. I don't think it was drawn here, but we are using the same thing, the same concept. Let me draw it for you in less than a few seconds. Itakuwa nimejora. We have force of 120 newtons. Cross-section area is 0.006 meters square. And on the same level, you see, on the same level, we have a load to be lifted up. This load, we need to calculate it. Then the area here is 0.5 meters square. So in this case, we simply just put our normal formula that there is no way you can study pressure in class. Then you tell me that you don't know that F1 over A1 should be equal to F2 over A2. In simple terms, what does this mean? It means that the pressure produced here is the same as the pressure on the other side. Even if it has a larger cross-section area, the pressure will be the same. And the load automatically will also be different. Now, 120, let's just replace direct. This one is complete. So we are going to have 120 over 0.006 to be equal to 120 newtons divided by, load over 0.5 meters square. So make L the subject of the formula, just cross multiply. So L is going to be 120 times 0.5 divided by 0.006. And you realize that our load is going to be 10,000 newtons. still mark it for yourself. Kama ulipata hiyo, kama hukupata, make the necessary correction. Allow me to move here very fast in question that follows. Give two properties which make oil suitable for use in a machine or in this machine. It's an hydraulic. Number one, oil does not corrode the parts of the system. Oil does not corrode the parts of the system. Number two, it is incompressible. Oil is incompressible. Oil is incompressible. It has a low freezing point and a high boiling point. That is oil. Low freezing point, high boiling point. Yes. Another question, question 5 now. Question 5. In an experiment to demonstrate atmospheric pressure. In an experiment to demonstrate atmospheric pressure, a plastic bottle is partially filled with hot water and the bottle is then tightly corked in a fungwa kabisa. It cannot allow anything to get out or in. After some time, the bottle starts to get deformed. State the purpose of the hot water. You put hot water, or alternatively, you put cold water, then you heat from the bottom. But the best thing is just put hot water. Hot water, I'm giving you the answer now. Hot water has steam that drives out air inside the container, and a partial vacuum is created. When the container is cooled. It drives out air, then when the container is cooled, a partial vacuum is created. Explain why the bottle gets deformed. To deform, it crashes. Why it gets deformed is because of the higher atmospheric pressure outside. Higher atmospheric pressure outside crashes the container inwards. That's why it gets deformed. To deform is to crash. Yes. Let me clear the board so that we can work on question 6. A very nice question here. It's a question that requires us we derive. Given that a container has a cross-section area of A and contains liquid of height H, whose density is rho, show that the pressure due to the liquid column is given by rho GH. For example, we have this liquid container, cross-section A, then the liquid is of height H. So we have been told show that pressure in liquid is given by rho, G, and H. We need to show that. It's a very common question to show that. That is, derive that. It's a very common question actually. First of all, we start by getting the volume. Volume is A, the cross-section area times the height, volume of the liquid, AH. Is it liquid or water? They have just said liquid. Then from there, of course, any liquid can apply. Now from there, we calculate what? The mass. You know, density is given by mass over volume. If you want to get mass, it is volume times density. Now, if you want to get mass, it is volume, which is AH times the density. That is the mass. So you see, we move from volume to mass. Now we are going to weight. You know, if you want to get weight from mass, you multiply by G. Weight is equals to A H rho. You get me? Now we have there's something I'm not providing. G. I've said that if you want to move from mass to weight, you multiply by gravitational field strength G. Now we have weight. Weight is the same as force. So when somebody says that pressure is force over area, it's the same as saying pressure stroke weight, because weight is a force. Now it's going to be A H rho G over A. Then the A cells. We remain H rho G. We are almost there. This is not the answer. Angalia swali. Swali imesema H. Oh, it's well now. I was looking at the way those values has been paraded. If we have said show that P is equals to H rho G. Now in our question, it have said show that pressure is H rho G. So that's where. If they had said show that pressure is rho G8, you have to say is equals to rho G8. So depending on the question, panga kulingana na venye examiner amepanga. In our case, amesema H rho G. So we stop here. H rho G. Yes. The figure below, we are at question 7. Now ukiwa na swali, unajua my channel has many teachers following it. If you have a question, just on the comment section, ask the question. You will see how many people will attend to you. The figure below shows a long tube filled with water. The open end is then covered with a cardboard and the tube is inverted. It is observed that the water in the tube does not spill out. Explain this observation. Explain this observation. I will explain to you. I'm not an artist, but I always try to draw good things. More than some of you who are doing art. So you get this. Explain why the water will not get out, will not spill out. And it's a matter of pressure. In the cardboard, they have used a cardboard here. Wanaandika cardboard. Oh, inaandika cardboard. You know, if the pressure inside is greater than outside, then this cardboard will get off and the water spill out. But now they cannot spill out because the pressure inside the tube is less compared to the atmospheric pressure outside. That's why the water will not spill out. If you just tell us that the pressure outside is greater than the pressure inside, you're well. Mark it for yourself. Another one here. There's another one here I want us to look at. The figure below shows here's apparatus. It resembles the first one, but allow me to draw it again very fast. Allow me to draw it very fast. Allow me to draw it very fast. We have two liquids. We have two liquids there. We have liquid X. Then we have water. The level of water, it is 30 centimeters. And the level of liquid X is 25 centimeters. Again, we have been given an additional information here. We are told water has a density of 1 gram per centimeter cubic. Also, it was not necessary because as a student, you must always know that the density of water is 1 gram per centimeter cubic or 1000 kilogram per meter cubic. So there is no need to be given, but because I don't know, because of what you have been given it well. Now find the density of liquid X. So you see, because all of them are connected to a common source of pressure, then it means the pressure are the same. What makes the height to vary is because they are different densities. So in a very simple term, allow me to say rho GH of this is the same as the rho GH of liquid X. So rho GH, ndaweka hapo that will do for water, is equal to rho GH for X. Now let's replace what are replaceable. 1 gram per centimeters cubic is 1000 kilogram per meters cubic. Why am I converting to 1000 kilogram per meters cubic? Because it is the SI unit of density. So I will have 1000 times G is always 10 times H. 30 centimeters, make it meters. 0.3 should be equal to density of X times G, which is 10, times H is 0.25. From there now, we no longer have physics, but we have mathematics. So what happens is, give us a full value of this. You will realize that it is 3000. 3000 equals to 2.5 rho X, or density of X. Then divide across by 2.5 by 2.5. You will have this. You will have 1200 kilogram per meters cubic, which is the same as 1 gram per centimeters cubic. Any of the two qualifies to be the answer. Ask yourself. In fact, after doing it, you really know whether you have gotten it right or not. If the length or the height, if the height of the water is small, it means its density should be greater than the density of water, and that's exactly what we have gotten. So it's that way. Yes. Explain why water dams are built with thicker walls at the bottom than at the top. These are some engineers. Some engineers. I remember some few years ago, a dam in Nakuru, Solai, passed, and the water were all over. Somebody was sleeping, anaamka ako juu ya meli, amepepwa na meli. Si meli, ni nyumba imekeuka meli. Simply because maybe there is something that was not done well. A dam should be this way. The bottom part, upande wa chini, should be greater than the upper side. Reason is, pressure at the bottom is greater than the pressure at the top. So, thick walls are necessary to withstand the greater pressure at the bottom of the tank. Ukijua kuna shida, hata ikiwa very thin, the pressure is very small. But at the bottom, remember, pressure in liquids increases with depth. So therefore, what do we mean? You should increase the thickness to withstand the greater pressure. The diagram below shows a setup used by a student to show variation of pressure in a liquid. Use it to answer the questions that follow. State and explain the effect on the height edge when the dissolved funnel is moved downwards towards the bottom of this funnel. It's a very simple thing. So this is how it is. So I'm saying this. State and explain the effect on the height h. This height. State and explain the effect on the height h when the distal funnel is moved downwards towards the bottom of the liquid. Towards the bottom of the liquid. When you move this downwards, the height h increases. Reason is one, pressure in liquids increases with depth. Pressure in liquids increases with depth. That is it. Another, many diagrams, a lot of diagrams. But I will manage. Let me just draw it very fast. I hope you are seeing what I'm trying to do on the board. Question 10, we are almost there. Don't tire up. Sorry. So I hope you've been looking at what I've been drawing. Now, we are told to find the value of height h. Please listen to this. They are not of the same levels. They are not like the other one I have drawn. They are not of the same levels. So meaning what? If they are of the same levels, if they were of the same levels, we just equate them rho gh directly. But now here, we have rho gh, then we have force over area at this point. So now this particular 120 kilograms is so strong, it can lift the liquid at the height h together with 40 newtons on top of it. So what are we going to do here? I will do this. I will make it very simple. I will say 40, just follow me, 40 over the area. It has been given in centimeters square, but I want us to give in SI units. You divide by 10,000, you get 0.0025 plus what? Plus rho gh height. This, they are not of the same levels. Plus rho gh. Now, those two should be equal to force over area of piston B, which is 120 kilograms. Can you make it newtons? It gives us 1200 over. It gives us 0.008 meters square, because we are converting it to the SI unit. Then from there, allow me just to give you directly the way it will be. This one will give you 16,000. 1,000, yes, plus, we have to bracket, no problem, plus 80. 800, that is times 10 times h. Density, gravity, h, atuna, should be equal to, ile ingine itakupatia 15,000. No, 150,000. And because you also have a calculator, and please let me tell you this, Form 1, you are supposed to use a calculator now, no problem with that. If you are my student or if you are in the school I am, please come with a calculator next time. This one should be 150,000. Now it's becoming very simple. Oh, take this, the other side, go and subtract this from the other side. In positive, again, the other side in a negative, in a 134,000. Now in 8,000, same 134,000 after subtracting this, divide by 8,000, you will get 8 to be 16.75. Don't write centimeters, it is meters. It is meters. It is meters. Kuna mtu alifanya bila kuconvert hii na hii, you will still get in centimeters, you will get 16.75 centimeters. It's actually okay, but please let's work with SI units. Thank you, we are almost there. I know you are tired. You want to go and sleep and have some fun. Kwani sifiki diagram ilikuwa imechorwa? Oh, it's here. Gas is getting in, or there is a gas. We are measuring the pressure of a gas using a YouTube manometer. YouTube manometer is used to measure the pressure of a gas. Mercury barometer is used to measure atmospheric pressure. So it can erase the mercury by a height h, and because it is not closed, because it's not closed, the gas pressure is rho Gh at this height plus atmospheric pressure, because atmospheric pressure is pressing it downwards that way. Now in this case, the first question is, if the atmospheric pressure is 750 millimeters of mercury, if the atmospheric pressure is 760 millimeters of mercury, what is the pressure of the gas in millimeters of mercury? So hapa kuna atmospheric pressure, then we have in 45 centimeters. First of all, convert this 45 centimeters in millimeters. My very simple mathematics is telling me it is 450. Then plus the atmospheric pressure, it gives us 1200 millimeters of mercury. As what? As the atmospheric, as the pressure of the gas. When I'm wrapping the pod, I'm giving you time to subscribe to my channel and to share that link to somebody. You want that person to also pass in pressure. By the way, these questions, if you just understand all these questions that I'm doing, you will just be well. Now, after giving our pressure in millimeters of mercury, which is 1200 millimeters of mercury, now we are told, can you give it in pascals? Pascal is the unit of pressure, just like Newton per meter square. Already we have the pressure in millimeters of mercury, so we just say pressure is given by rho, G, and H. So pressure is given by rho. The density of mercury, 13,600. Gravitational field strength here on Earth, I will go to moon, I'll come back and tell you what is the gravity there. Times 10, then times H. H is 1200, but now it's in millimeters. What will I do? I will just divide by 1,000. Then use simple mathematics. You will realize that it is 163, 200 Newton per meter square, or somebody will talk of pascals. You see, si mbaya sana. Yes. Let's continue. We are at question 12. Let me give you hope. We are going to question 21, not question 12. Now let's move very fast. Let's say, I will just wrap it. Next time I will have a personal assistant who will be doing it for me. Ndakuwa na kazi yangu ndio kufunza, kazi yake ndio kufuta ubao. Kazi yangu ndio kufunza, kazi yake ndio kufuta ubao. That vacancy is there now. You can apply it. Mtu wangu akunifutia ubao. Ndakulipa tu. Haina shida. I will just pay you. Kisikia mtu mwenye anataka kazi ya kufuta ubao, ndakulipa. Na sijawahi pata, nimetafuta saa hii. two liquids, A, then we have liquid B of different densities. This one is 1 gram per centimeter cubic, meaning it is water. Hii ingine tumeambiwa ni 1.5 gram per centimeters cubic. Sasa we are told calculate the pressure exerted at the bottom of this container. Because the liquids are different of different densities, we are going to have rho GH mara mbili. Ingekuwa tu ni moja tungesema tu rho GH once, but now because there are two, let's have it done twice. Tuanze na hii, then tuende hii. So it's going to be rho GH of A should be plus rho GH. This one is B. Tuanze na A, no problem. Rho is 1000. I know you're wondering why. Si nimeconvert hii yende nini? Yende SI unit times 10 times 0.4. Mbona nimeandika 0.4 na sio 40 in SI unit still. Plus rho of now liquid B, 1500. 1.5. You know, if you want to convert from grams per centimeters cubic to grams, to kilogram per meter cubic, you multiply by 1000. Times 10 times 0.25. Watu wa Mungu tumefika hapo. Hii ni 3750. Hii ni 4000 plus 3750. Now, use the calculator your parents bought for you. You know, see how now 7750 Newton per meters square. That is where we are. Kama umepata hiyo, si ufurahi tu sema at least nimepata hii. A small nail, now listen to this, a small nail may pierce an inflated car tire and remain there without pressure reduction in the tire. Explain the observation. Ukiona imedunga, hata kwa volleyball, you always play volleyball. Sindano ikidunga mpira and you still want to continue playing, don't remove that sindano. You just shape it, ikae hapo, so that mkimaliza mtoe, then now the pressure will reduce inside, then you mend that hole. Now, it's the same thing as this. It will not get out. The pressure will not reduce. It is a very simple thing. Inside the tire is an elastic rubber. Yes, inside the tire is an elastic rubber. The pressure inside the tire stretches the rubber to grip onto the nail. The pressure inside the tire stretches the rubber to grip onto the nail firmly without allowing air out. It's because of elasticity of the rubber inside the tire. That is it. State two factors affecting pressure in liquids. I'll give you three. If they ask two, by the way, if they ask two, start with the density of the liquid, depth of the liquid. Most of you give height. Height is not much encouraged. Give the depth of the liquid. Then if they ask three, ongezea gravitational field strength. But if they ask two, now the particular gravitational field strength, I will fail you. But if they ask three, it is correct. Look at this thing. We have two pages there. The first one and the second one. I hope my pen is not too much faint. Most manufacturers prefer the first one over the second one. If these parts are equal, if those two parts are equal, they prefer this over this. You know, kama maji yenye imejaa hapa, sema hapa ni 60 centimeters. The same amount of water, nikiweka kwa hii ingine, itaenda mpaka 100 centimeters. Now, they prefer this over this. Why? Write this. To reduce the height of the liquid. Not liquid, to reduce the height of the pail, but maintain the capacity. Reduce the height of the pail, but maintain the capacity. This reduces the pressure exerted by the liquid. This reduces the pressure exerted by the liquid at the bottom of the pail. At the bottom of the pail. So it will not destroy the pail and where you are placing the pail. But this one, it will get destroyed very fast, and it also destroys where you are placing it. Explain why trucks carrying heavy goods have many wheels. That's another similar question. Many wheels increases the surface area in contact with the road. It increases the area in contact, or the surface area in contact with the road, hence reducing the pressure. In a braking system, why is the master piston made smaller than the slave piston? Why is the master? Remember, it is the master piston that starts being pressed. Now the slave piston is later on. So it is made smaller. In short, you are being told why is its cross-section area is smaller, to create or to generate a high pressure that is going to be transmitted equally to all the other parts, to generate or to create a higher pressure. Nice. Look at this figure below. I hope it is. Kama yonagani you zoom. I don't know how you zoom it, but it's out. Explain when the piston is pulled upwards, valve 1 opens and valve 2 closes. Valve 1 opens. Explain why when the piston is pulled upwards, it opens and this one closes. You know, when you pull this upwards, a less pressure is generated at this chamber, allowing water to get in, opening valve 1. When the water gets in, valve 2 on the other side will have to close. You know, these things, they take place simultaneously. When this one is opening, that one should be closing. So now if valve 1 is closing, that one is opening. So when you pull this upwards, you create a less pressure region in this chamber, allowing water to flow upward, opening valve 1. And when water gets into this chamber, it's called the chamber Y. When water gets into chamber Y, you see, this okay, because less pressure has been created here. So water from outside here, from the well now, gets in and then opens. Then this water also will flow to this part actually. Before now they move back, again they will flow to this particular chamber. From this chamber X, from water lower in valve 2, they will also flow to this particular part. And this one, because there will be no water pressing it, it also closes. But when we press it downwards, water rests on valve 1 and it closes. And the only entry is to get to valve 2, which will open. So it takes place at that particular point. Explain how continuous flow of water is maintained. Andika imali. Nakama ulipata, you mark it for yourself. It is due to compressed air. It is due to compressed air that expands, ensuring a continuous flow. It is due to compressed air that expands, ensuring a continuous flow. State one advantage of force pump over lift pump. State one advantage of force pump over lift pump. You know, we have force pump and lift pump. And by the way, the following are the applications of pressure. And I will not force you to read, but let us who will do it. Read about hydraulic brake system. It's one of the applications. Force pump, lift pump, bicycle pump, then siphon. State one advantage of the force pump of a lift pump. It enables continuous flow of water, as we have said. The height to which water can be lifted does not depend on atmospheric pressure. Does not depend on atmospheric pressure. Let's go to question 17. Oh, yeah, it's clear. A block of glass of density 2.5 grams per centimeter cubic has dimensions 8, 10 by 15 centimeters. It is placed on one of its faces on horizontal surface. Calculate the weight of the block, then the least pressure it can exert on the ozone surface. The least pressure requires the maximum area of contact. The maximum pressure requires the least area of contact. Now, 8 by 10 by 15. First of all, let's calculate part A. Amesema actually I don't know what I'm doing. I just really need the majority. 8 by 10 by 5 or by 15 centimeters. Tumeambiwa this particular glass block has a density of 2.5 grams per centimeters cubic. Grams per centimeters cubic. Grams per centimeters cubic. So calculate the weight. Calculate the weight. So kitu ya kwanza, let's get the mass. Do you know what? Volume of this particular block is given by 8 times 10 times 15. Which gives us, is this 150 times 8? Is it 1200? Yes, it gives us 1200 centimeters cubic. Now density is 2.5 grams per centimeters cubic. You know what? Density is given by mass over volume. Mass is given by volume times density. Are you getting it? Then we have the volume as 1200, density as 2.5. Multiply the two. What will be our mass? You multiply with this as per our formula. What will you get? Come on a calculator. What will you get? You will get 3,000. So our mass is going to be 3,000. 3,000 is it grams? Yes, grams. But the question is not asking about mass, it's asking about weight. First of all, let's make this kilogram. How do we do it? We divide by 1,000. We get 3 kg. Still, that's not the answer. Multiply by 10, you get 30 newtons. How many have 30 newtons? So, listen to this, question 18. We are almost there. Compare to number 21. I'm giving you hopes where there is no hope. There is light at the end of the tunnel. Na uchunge usione light ya nduthi ufikirie umefika at the end of the tunnel. A piston whose diameter is 1.4 meters is pushed into a cylinder containing a fluid. If the pressure produced in the cylinder is 4,000, is 4 times 10 power 5. 4 times 10 power 5. 4 na 0 stand 400,000 pascals. Calculate the force applied on the piston. Now, nikuulize, you know what? Oh, question 17, there is part I did not calculate for you. Question 17, part B. Calculate the least pressure. Still, okay, allow me to take you there. I don't know why. 30 newtons is the weight, which is acting as the force. Then, the dimensions were 8 by 10 by 15. 8 by 10 by 15. What can you do here now? Because the question wants us to give the least pressure, we pick the maximum area, which is 10 times 15. 10 times 15 is 150 centimeters square. Or, let's give it in meters. 10 into meters is 0.1 times 0.15. So our area is going to be 0.1 times 0.15. This one you get 0.015 meters square. Then the pressure is going to be 30 newtons over 0.015 meters square. You get what is going to be your pressure is going to be 2000 newton per meter square or 2000 pascals. Tuko pamoja? Sorry, nilikuwa nimeenda question 18 mpaka nikawapea hopes at the end of the tunnel. Unajua wanasema kuna light at the end of the tunnel. Saa zingine unachanganywa na light and uthi, unafikiria umefika at the end of the tunnel. Diameter is 1.4 meters square. Oh, meters. Oh, diameter cannot be square. Is pushed into a cylinder containing a fluid. If the pressure produced in the cylinder is 4 times 10 power 5 pascals. Calculate the force applied. Unajua sasa we always say that pressure is equal to force over area. Ukiandika hivyo kwanza ukiandika hivyo utapotea 1 mark. Hata kama utaachia hapo tu, wewe ni mtu uko na akili. Here we don't have area. The one we have is diameter. So you just find cross section area pi r square. Pi r square. Just do your pi r square. I don't want to do it for you here. Then pi r square, and the r is 1.4 divided by 2, but the 0.7 pi r square. You'll get 1.5394 meters square. Then the pressure given is 400,000 pascals. 400,000 pascals. Make F the subject of the formula because they want you to get the force. It is. This is 400,000 and this is 1.5394. You will get 615,752.16 newtons. We are on our last page, by the way. Hakuna ingine nikimaliza hii page ndivyo. Sawa. I'm trying to see if I can find whatever I'm looking for. Lakini sioni hiyo kitu natafuta, lakini napata siku nyingine. The figure below shows a rubber sucker. Explain why the rubber sucker sticks on a clean surface. Rubber sucker inakaanga hivi. I don't know if majority kitu funny. Inakaa your shoes. When you press on a flat surface this way, when you press on a flat surface, it drives out any air. It drives out any air which was inside. Then, if there is no air inside the rubber sucker, now the pressure outside, which is the atmospheric pressure, becomes greater than the pressure inside. And when you try to pull it, it sticks on it. Why? Because you have to overcome the atmospheric pressure so that the rubber sucker can leave the flat surface. So let's summarize this way. Explain why the rubber sucker sticks on a clean surface. Because to remove the rubber sucker from a clean surface, from a flat surface, you have to overcome atmospheric pressure outside, which is greater than the pressure inside the rubber sucker. Ukiandika hivyo hakuna shida. Come here. The figure below shows how empty water from a large tank into a low-lying container using a rubber tubing. Yes. Pressure difference between points A and D. We are supposed to find the pressure difference between point A and D, but before that, explain why the tube must be filled with water before emptying process starts. Hey, now this one. Kuna watu wanasema to provide continuous flow of water. Hiyo huwezi pata. Nikikutana na karatasi yako atumeandika to provide continuous flow of water, I will give you wrong. On top of that, I will look for you. On top of looking for you, I will deal with you dangerously. I will beat you. You are not supposed to say, okay, start this way. If you must write that sentence, to provide cohesive force that gives continuous flow of water. To provide or to give cohesive force that provide continuous flow of water. Pressure difference between point point A and B. It's because of this height. It's because of this particular height. Rho GH of this point. And in this case, we have 7.5 times 10 times 1,000. What's 1,000? The density of the liquid is in water. Can you check it? I think I said it is water. Yes. So rho GH. So you will get it at 75,000 pascals, Newton per meter square. The pressure experienced by the finger, if you put a finger at this particular point, it will experience pressure mara mil. Rho GH of this 7.5 meters plus atmospheric pressure that is exerting on part A. You know, part A is pushing this water to rise this way. Now when you put your finger here, you are experiencing two kinds of pressures, that is rho GH, then atmospheric pressure. So you will take our answer here, A, which is 75,000 plus the atmospheric pressure. Atmospheric pressure, okay, we can calculate the atmospheric pressure. Let me try to find out the atmospheric pressure if we are given or not. Oh, we are given the atmospheric pressure to be 76 centimeters of mercury. So what can we do? We calculate the atmospheric pressure in terms of pascals. So it's going to be 103,360 plus 75,000. You get your answer. I will not take you back at the final stage. Just 103,360 plus 75,000. You want to tell me you cannot get it? Mark it for yourself if you have that one. Now, lastly, the last question, which I want us to finalize with. Yes. Yes, we have mercury here. First of all, tunaambiwa name part labeled X. It's a vacuum. It's a vacuum, but now you don't just say it's a vacuum. You give a special name. It is called Torricellian. Torricellian vacuum. Torricellian vacuum. Torricellian. Torricellian vacuum. State and explain the effect on the height h when the barometer was taken to a point on top of the mountain. The height h will decrease. Why? Because atmospheric pressure at the top of the mountain is low. Explain the test that will be made to find out whether such a barometer has any gas in the space above the mercury. By the way, it's supposed to be vacuum. If a gas is present, then it means what? That particular mercury barometer is faulty and it's not fit to be used. You slant the tube. You slant the tube. If the mercury fills the barometer, it's okay, it's not faulty. But upon landing, if the tube, if a space is still left, then it is air. And that one is to say it's a faulty thermometer. Please, it was just a simple paper. And by the way, this paper was done by Nyahururu Girls High School as the contest. If you see any teacher from that side, be hi. Now, mark it for yourself. Good. Those who have not interacted with the questions, no problem. Next time. Then I wish you all the best. If you have watched till this part, you are a hero in physics. And I'm telling you, pressure will never give you any problem. I wish you all the best as you are planning for your future, as you are nurturing your talent, and as you want to make your mom and dad proud. This is Sir Alex. I'm glad to be leading you in Ambassador Foundation that you may make it great in physics and chemistry. Next time, I will add more subjects. God bless you.